Good morning. This is Edwin Carlin giving the Meettechniek course this year, 2013, for the University of Twente in the Netherlands from the University of Tsukuba in Japan. This is last lecture in this year's Meettechniek course, and in fact, this is the last lecture of the Meettechniek course at the University of Twente. Today, Monday, 13 January 2014, I'm going to talk about temperature sensors and measurements, which include a little introduction on the thermal domain and a little bit of thermal domain modeling, elements, etc., which are similar conceptually using lumped modeling as mechanical elements, as hydraulic elements, as electrical elements. And then in the second part of the course, I will talk about some electrical measurement techniques, specifically digital multimeter, how it works, the importance of choosing the correct range to minimize measurement errors, an oscilloscope, basic operation, and then the importance of choosing the correct probe. And then at the end, we'll quickly go over the big functionality of a spectrum analyzer. Some administrative things first. Homework 9 is due today. There will be a strict deadline for the homework because I will post the solutions for homework 9 on Blackboard on Tuesday morning, 14 January 2014, so that all of you have some time to look at the solutions. There will be one exam question from lecture 10, and it will be on the material related to temperature sensors. I will give a more detailed explanation of the contents of the final exam in an announcement after the lecture on 14 January 2014, Monday. And also by Wednesday, 15 January 2014, I will have all homework grades posted. And if you're not sure about why you received a particular grade on a particular homework, please send me an email. I did my best not to make any administrative errors on calculating the homework grades, but in some cases this year, homework submissions through email consisted of some errors. So some submitted homeworks didn't have all of the solutions in them. So the grade that was received was lower than some students thought it should be. We corrected that as we went through the course. But if you see that your grade is lower than what you thought on any particular homework, please send me an email so we can discuss why. It is very important that you try to do all of the homework problems and study the homework solutions. The final exam will be based on the homework assignments and the solutions. And in some of the homework solutions, I also describe in more detail other types of problems that we could solve using these basic techniques. So if you want to do well on the final exam, then I recommend to study the homework problems and the homework solutions. The homework will not contain the exact problems, but it will have, in essence, 7 or 8 of them directly from the homework. I will ask some similar questions as the homework, and I will also ask some additional questions. But if you did the homework and you studied and you understood the basic calculations that were done, and all of the calculations are quite basic, then you will have no problem in being able to go through the exam and making all of the calculations. So the final exam will have between 8 and 9 problems, and I will give some more details about what you need to study for the exam. And as usual, for the exam, you can come prepared with the blue books. We will have extra paper that you can use to make some calculations. Um, you don't necessarily, so you cannot bring a programmable calculator. You can only use a calculator to compute numbers at the end. But in reality, you shouldn't have to use the calculator until very much at the end of the class. So you cannot program your calculator or your own to have all of the solutions to the homework. That's not allowed. And if you do that, then it's considered cheating. Temperature measurements. Today I will talk about the thermal domain, thermoelectric sensors, which are also called thermocouples, thermistors, semiconductor, temperature sensing devices, and then radiation thermometers. Radiation being infrared radiation representing heat, which are common techniques to do measurements of heat without making contact to the heated element. Some definitions as we have done throughout the course. The transfer of heat is normally from a higher temperature object to a lower temperature object. We all know this from practical experience with hot and cold temperatures, hot and cold objects, when we touch it with our fingers or this type of way. And then we're always dealing with the first law of thermodynamics that we saw earlier in the course, where we basically have conservation of energy within the system. So the change of energy within a system is due to the work that we put into the system. Okay. So the 4 quantities that are important for heat transfer in the thermal domain for this course are heat, which is given, the quantity is given the symbol QTH. It is a joule, is the unit. And this is analogous to electrical charge if we're going to be using these lumped models. Temperature is theta, which is Kelvin. This is analogous to electrical potential or voltage. The heat transfer rate or the heat flux, which is Q dot TH, which is dt, dq TH dt, or dx, I'm sorry, in space, not time, and that's joule per second. This is analogous to electrical current. And then Fourier's law gives us the heat rate is proportional to the gradient of the temperature. And this is analogous to Ohm's law. Let me go back to the heat transfer rate. Q dot TH is the time derivative of the heat. So this is joules per second. I'm sorry, I made a mistake on this. And this is analogous to the electrical current, which is dq dt. So these are the 4 quantities that we will be working with to define the thermal domain, which are quite important for electrical engineers to know. Okay, so elements, thermal elements, as we have electrical elements, as we have hydraulic elements, we can define thermal elements in the same way. Heat capacitance, where the heat flow is equal to CTH times the gradient of the temperature. specific heat capacity, where you analyze the heat capacitance with a mass in kilograms. So you have joule kilogram per degree Kelvin or per Kelvin. Thermal resistance, RTH, then the gradient of the temperature is equal to RTH times the heat. And the thermal conductivity, GTH, which is essentially 1 over RTH, the thermal resistance. And they also have, with the thermal domain, the coefficient of heat transfer. And this accounts for heat flow across a boundary. And we use this most for something called convection. And it's one of the reasons that if you take your computer apart and you look at the microprocessor, you'll see this gargantuan slotted contraption or structure on the top of your microprocessor. This structure, these fins, is essentially to dissipate heat using convection. So you have a fan that blows, but also you want to increase the surface area so that you can dissipate the heat. And this H, this heat transfer coefficient, is related to creating a large surface area so the heat can be dissipated in a much more efficient way into the air. And the fan also increases this H so that it's larger so that you can pull more of the heat out of the microprocessor and put it into the ambient air. In thermal elements, then, our heat capacity, conduction, conductivity, convection, the heat transfer coefficient, and radiation. And there are some other symbols that we'll use for radiation that will be introduced a little bit later in the lecture. Heat capacity, it really relates to the amount of heat an object can store. And this is the definition of it, and where is capital M is the mass in kilograms, and small c is the specific heat of a particular material. Now, thermal energy may be transferred from one object to another in 3 ways: conduction, convection, and radiation. And all of these 3 mechanisms are shown in the picture on the bottom. So if we have a heat source that's located on the left part of this slab that contains 3 materials on top of the heat source. Now, if we have a heat source, it's going to want to share its temperature with anything that's in contact with it. It's to get rid of its heat somehow. These 3 layered materials where we have a temperature drop from T1 to T2 to T3, and then T3 drops to a temperature at its surface. Okay, so the temperature of the heat source is going to be what we call dissipated or dropped across each one of these particular slabs. That's thermal conduction. And you can almost think of this as the conduction across here is like a resistance, and you're going to drop a voltage across a resistor. Here you drop a temperature across a particular slab. So you have a certain thermal resistance that's going to basically drop a certain temperature across it. So we drop from T1 to T2, T2 to T3, then T3 to the surface, right at the boundary of the surface. So what happens then is that the heat source, if we look at all the way to the right at slab number 3, this slab, which is dark gray on the right, is going to become warmer due to the heat source. Now, the heat on the surface of T3, on the surface of this slab number 3, so T3 is at the interface between slab 2 and slab 3. On the surface of slab 3, the heat can leave in 2 ways. Convection, where the heat actually just gets dissipated into the air. The heat can be dissipated much faster if you run a fan. So in your computer you have a fan to help with removing the heat from that surface. Also, you can create the surface area, increase the surface area, and that also helps to increase the convection. Now, any hot surface also radiates. Okay, it becomes electromagnetic radiation into the far infrared wavelengths. Okay, you can't see that with your eye necessarily, but it comes off as heat. So heat is actually being radiated. If you think of a lamp, an incandescent lamp that glows, it becomes hot. So this is thermal radiation. Anything that becomes hot radiates with far infrared wavelengths. Conduction, so the heat flow, which is equal to dQTH dt, is equal to this general expression. That's the thermal conductivity GTH. A is the interface area where the heat is transferring, so the cross-sectional area, times the gradient of the heat. In this case, we take the gradient in just one dimension, in the x dimension. But in general, you can do three-dimensional types of calculations with this. So you can have x, y, and z as well. And this is an example of the thermal conductivity of certain materials. And then as we can expect, if we look at air, the thermal conductivity, which is in the center, has units watts per meter per degree C in this case. Air, the thermal conductivity is quite small, and glass is about 10 times greater. Gold, for example, is about 1,000 times greater in this area. Polymers tend to be also very low, so metals and these types of things conduct heat very, very well, as we know. Now, thermal convection, you can read over some of this, but this is when you have slab 3 that's being heated at interface T3. At the surface of slab 3, it becomes warmer, and that heat will actually move to the ambient surroundings where you have the ambient temperature. So heat will leave the surface via convection. Okay. Now the general expression we have this Q dot TH is equal to alpha A, the difference in temperature between theta 1 and theta 2. Now theta 1 would be your heated surface, and then theta 2 will be your ambient temperature. Now alpha is the convection coefficient, and this is very much an empirical value depending on the geometry and what you do to your surface, whether you have natural convection or you have forced convection. Forced convection would be you literally have a fan in the case of your personal computer that's blowing air across the surface to increase this convection. So alpha, this coefficient, the convection coefficient, depends really on what you do to the surface in order to enable the heat to leave to go to the ambient. Now, in the case of a horizontal plate or a vertical plate, these are some empirical values for a horizontal plate and a vertical plate. This is kind of a black science in how we develop these surfaces so that you can convect and get rid of much of the heat. But it's important to know that that this type of heat transfer is quite important in order to be able to dissipate out into the environment. And the last element that I'll talk about today, or mechanism, heat transfer mechanism, is radiation. Essentially, if you have a surface, let's say slab number 3, and we have an elevated temperature above the ambient temperature, and if it's warm, we know that the molecules in this material, they're going to vibrate, and these vibrating molecules are going to emit radiation, right? Dipole radiation. We're going to get radiation from these vibrating particles. And in this case, due to temperature, the wavelengths are very much in the infrared, very much above 1 micron. Let's say even at room temperature, radiation temperatures at room temperature are in the area of 10 micron wavelengths. And this shows the spectral density at different temperatures. So most of these in the far infrared, you'll see between T1 and T4. Most of the radiation that we're dealing with is in this 2T2 region. So remember that room temperature, let's say 30 degrees centigrade or 25 degrees centigrade, is around 10 micron wavelengths. That's the radiation. And then we increase as we go to temperatures. Now, thermal radiation, we can use the well-established temperature to the fourth power relationship, and sigma SB is the Stefan Boltzmann constant. And this value sigma, epsilon, is emissivity. And emissivity is essentially a parameter, a material parameter, that describes how well a surface can emit radiation. So a small emissivity, much, much less than 1, close to 0. So emissivity is between 0 and 1. So small emissivity means that not a lot of radiation can be emitted surface. If we have epsilon equal to 1, that's a perfect emitting surface. This is a black body. Okay, this is actually quite difficult to achieve, a perfect, or an epsilon near 1. And most materials are, of course, less than 1. And this is an example of some materials in the radiation emissivity. So an ideal black body, your epsilon is equal to 1. It's quite interesting that if you look at gold, gold is quite a bad temperature radiation emitter, 0.02. Glass, on the other hand, is quite high, 0.95. So although gold is a really good heat conductor, it's a really, really poor heat radiator. And so you can see some different values of snow is also quite good, 0.85. And water is even better than glass. So it's kind of interesting to see some of these different emissivity parameters depending on the material. It's not always matching with our intuition of the materials. Okay, so we have now, I have defined some of these parameters. Now let's just do a simple example of using these thermal domains. And please note that I'm using, in this example, T as temperature rather than capital theta. For most of the rest of the lecture, I use theta, but in this example, I didn't change the slide, so we're using T, so just be aware of that. So in this example, we have a picture located on the top, and then the picture on the left. We want to use a sensor to measure the object temperature TB. And we put a sensor, this is a contact type of sensor, we put a sensor physically in contact with the object, and then the sensor is connected thermally to the outside environment. So this is just our ambient temperature, our room temperature, whatever it is, T0. So what we want to do is we want to make a model of how does the sensor being in contact with the object, how does that affect reading that you get from the meter. So when you put the sensor on the object, does it affect the temperature? It must, because it must change the thermal circuit. It's like using an oscilloscope and using a probe to probe your circuit. Now the probe becomes part of your circuit, so it's going to affect what you read out. So we can model this now because we have these elements. We can use lumped element modeling. And lumped element modeling, remember, is we use resistor, capacitors, and resistors, and then we can use Kirchhoff's current and voltage law and differential equations, and we can analyze both steady state and time domain behavior of the different domains. Okay, So we want to analyze what is the temperature of the sensor, we're going to call that TS, um, dynamically. Dynamically, I mean with respect to temperature. I'm sorry, with respect to time. So we can create a lumped element model that's located on the right. So then we have TB, an object with a temperature TB. We have a finite thermal resistance that goes to the sensor head. And then we also have a resistance that goes from the sensor head to the ambient environment, and that's basically this little wire that you see on the left. The heat flow will go from the object to the ambient temperature through the sensor and then through this connecting wire. And then also there is a thermal capacitance associated with being able to, the sensor will take some time to heat up before it. Remember, the thermal capacitor is the ability of the material to heat up quickly. So it doesn't heat up instantaneously. So this thermal capacitance is basically a value that represents how well the material can heat up how quickly. Okay, now in steady state, let's say, we can just analyze this so we don't use this little capacitance value, the thermal capacitance. And then Ts is equal to TB minus T0 over these resistances. And then we can see that what happens here is Ts, this is the temperature that we measure, will be TB, the real object, minus some delta T, which is the resistor divider over these resistors. So we can never really measure the absolute value of this temperature. It's always going to be dependent on the material of the sensor and how well you can make contact to this. So this R1 is really sensor head and how well you can make a good thermal conduction path to minimize R1. So if R1 ideally is 0, then Ts is going to equal to TB. If R1 is quite large, then the temperature that the sensor gives you or tells you is on TB is going to be quite erroneous. Okay, so we can also do a dynamic time domain analysis. So we can analyze going back to our differential equation for the heat. dq dt is equal to G times A, thermal conductivity times the interface area. And then our delta T, TB minus TS. And then we also know that dq dt, the temperature dt, so this is the gradient, is equal to m times c, and m is the mass. This is the mass of the sensor head plus the connecting wires, times the specific heat of the material. So then we can rearrange this, and then we can separate the variables. We can get the temperature on the left side, keep the time on the right side, and then we solve this standard differential equation, which is basically has the form 1 minus epsilon, and then your time constants, just like an RC circuit. And then you can see that Ts is going to increase in the same way to TB minus delta T. So if you think of time going to infinity, then our epsilon minus T over tau 1 is going to 1. So then TB is going to be, or TS is going to be TB minus delta T, as we saw in the steady state solution when we first did it. But you can also see that it's going to rise with a time constant, delta T, or this tau 1. That's a function of the thermal conductivity, the mass, and the specific heat of the sensor head, and also the connecting wire that you see, this little wiggly thing that moves from the sensor to the ambient. So when we do temperature measurements, we have to be very, very careful on how we make contact to what we're measuring, of course, and then the materials that we're using. Luckily, temperature sensing is quite a well worked out area of measurement science, and over some of the techniques that are used in industry. Now, when we measure temperatures, okay, you can read over some of these general rules, but essentially, um, uh, when we make a measurement, we're going to be measuring the transmission of a small portion of an object's thermal energy to the sensor, and then convert that energy into an electrical signal. When a contact sensor, as we saw in the example, is placed on the object, heat conduction takes place between the object that you want to measure and your sensor probe. This little blob that we saw, the sensor, when it touches, heat conduction. So we want the heat conduction to be very, very good between our sensor probe and our heated object. Now, the sensing element in the probe warms up or cools down through the exchange of heat with the object. Okay, and we want this also, the sensor head, we don't want it to affect the temperature that we're measuring. So we don't want to pull too much heat out of the object. So we don't want a really large probe on a tiny little area, because then we're going to basically take all of the heat away from the object that we want to measure. So if we have a small object and we want to have a small probe, or even better, a non-contact type of measurement so that we don't affect. If we have an object that's very, very big, we can usually make a small sensor, plop on the surface, and we can do a measurement without affecting its global temperature. So this explains also some of the concepts here, and you can read this over. So a typical contact temperature sensor consists of the following components. It has a sensing element, contacts, and then an envelope around the sensing element to protect this from the surrounding environment. And these terminals on the outside are going to be the probes that are going to make contact to the element. And then you can see the example. This was a contact type of measurement that we used in our example. Now, a non-contact type of sensor, and this basically measuring thermal radiation, contains a sensing element that's responsive to the temperature. And this also has terminals, a sensing element, and then a transparent window to the thermal radiation. Okay. Conceptually, very, very simple, but quite powerful. So we have non-contact measurements and contact measurements. So depending on the type of situation that you have, you're going to have to choose which one is most appropriate. Now, thermoelectric sensors, these are the first sensors that we'll talk about. These are contact type of sensors. Now, the thermoelectric sensors are based on using two different types of materials, okay? And when these two materials are put together, okay, they're connected together, they create this EMF, this EMF, this electromotive force between the two of them. And when they're touched together, we get this EMF, which is then also a function of temperature. So we have these are called thermocouples, two materials, well characterized. We solder them together. They create a voltage. That voltage then is a function of temperature. With the right choice of metals, these can be extremely, extremely linear functions of temperature and very stable, which is why they're probably the most commonly used sensors in industry, in laboratories, generally inexpensive. You can buy them very, very cheaply, and they're quite successful. And the little equation on the bottom shows that the EMF, depending on what kind of temperature range you need, that you can expand this voltage which is dependent on the temperature, into this kind of like a Taylor series. But in most cases, pretty large temperature ranges, we can just use this, the first order approximation where the EMF is approximately equal to some calibration constant A1 times the temperature. That's our transfer function. Our transfer function in this case is our output is the voltage, our input is the temperature, and the transfer function is then just this constant. So as I said, these are thermocouple sensors. These are called thermocouple sensors. And the images on the bottom, you can see this is a J-type thermocouple. When you weld these two materials together, we have an iron and a constantan. When these are welded together, then they generate this EMF, which is a function then of temperature. And the picture on the right shows an example of doing a readout measurement. And this is you can look over this diagram to see how you have a hot junction and a cold junction, and you can do a calibration for this. So the picture on the right, if you're doing these types of measurements, typically you will use a cold junction and a hot junction. And this picture just shows how to do this. This is a very standard thing. You can look at this diagram to get the basic idea from this. So how do they work, thermocouple sensors? Now, as I said, when we join two materials, let's say A and B together, they will generate a voltage, this EMF. This is called a Seebeck voltage, VAB. So when we weld the two materials together, they generate a voltage, which is dependent on temperature, and then we can expand that temperature using a Taylor series. And you can see that's what we've done here. We say VAB is equal to beta 1 times the temperature difference plus the square of that, etc., etc. Take the derivative, and then we get this alpha term, which is called the Seebeck coefficient. And this is a diagram of a thermocouple sensor, and then we can analyze this. Now, this diagram, these thermocouple sensors, will probably see something like this on the final exam. So practice actually making some of these calculations, because most likely you will see something like this on the final exam. So in this case, we have material 1A, which is in red, material B, which is in blue. When they're joined together on the left, that's going to be our sensing head, and then both of these are connected to material which is in black, and then those are going to be at temperature 2. So that's our cold junction, and then our hot junction is going to be T1. The voltage VAB that we then is going to be this VAB is equal to beta 1 T1 minus T2. So we remember that we're typically using just the first order, the first term of the Taylor series, which has this constant depending on the two materials that you have and the temperature difference. And then the Seebeck coefficient is basically, if you go to a data sheet for particular types of materials, you'll see the Seebeck coefficient, so you can plug these in directly. Now, thermocouple sensors, there are many different types of materials. This is giving some common materials. They're typically made of alloys, so alumel, which is nickel, this composite material you can see, and then chromel, which has nickel chrome, and then constant has copper and nickel, and nitrosil, which has nickel chrome silicon, etc., etc. Now the noble metals, platinum and tungsten, and the noble metal alloys also have some of these materials. And also, so these different types of materials then have a particular letter associated with them. And the letter basically gave temperature range and voltage range that you want to convert. So type K is chromel, alumel, for example. And these are the calibration plots for different types of thermocouple sensors. And you can see on the x-axis we have temperature that we want to sense. And on the y-axis then we have the voltage dependency. And you can see in all of these are measured characteristics from a data sheet. They're extremely linear, so we can essentially ignore the T minus, T1 minus T2 square terms from the Taylor expansion. These are examples of tables for different type thermocouples, type E, J, K, N, S, T, and then the type is located in the upper left-hand corner. So you can see here in the left column you have the particular temperature, which ranges from minus 270 to 380. And then in each column you'll see what voltage each temperature will give for each different type of sensor. So if we're given a sensor configuration that has material A, material B, and then it's connected to material C, and then it has a cold junction, let's say T3 and T4, and then the sensor area where the two A and B are joined together, T1. How can we determine what the output voltage will be with respect to temperature T3, T4, and T1? So essentially what you do is you take the voltage drop VCA multiplied by T3 plus VAB at T1 plus VBC at T4. So each one of these junctions will give you a voltage drop. And that voltage is going to be sensitive to a particular temperature. So then we can also say that VCA at T3 plus VAB at T1 plus VBA at T4 plus VAC at T4. So BC was expanded into BA plus AC. Now, in the next line, VAB at T1, okay, minus VAB at T4. Now remember, we had VBA at T4. When we take VAB, it's going to be the negative of that. And then we have plus VCA at T3 minus VCA, which at T4. So we had VAC in the line above that, T4. And now we have VAB at T1 minus VAB at T4. So then we can bring these two together. We can say that the temperature difference T1, T4 between those voltage has the Seebeck coefficient AB, which is well known for material AB, for example. And then we can do the same thing for VCA between T3 and T4. We can get a Seebeck coefficient alpha CA and T3 minus T4. So if you see this problem, then we're going to be analyzing this, and then we'll basically calculate a temperature that we expect, or what kind of voltage do you expect if you had temperature T3, T4, and then T1, what kind of voltage are you going to generate if your Seebeck coefficient is this? So there are different types of thermocouple assemblies. Bare, twisted, you can look over these. These are just some details that you can inform yourself in case you want to measure temperature in the future. Another type of resistor is called a resistive thermometer. These are also called resistance temperature devices, RTDs. And they rely on the principle that the resistance is a function of temperature. So the resistivity of the material, which depends on the concentration of free carriers and their mobility, etc., is a function of temperature. So typically we use materials like platinum is quite a good one, copper, nickel, and tungsten. Now, the platinum thermometer, for example, has an extremely linear relationship depending on the type of platinum that you use. So you can see also that we have this expansion using a Taylor series, but usually we use the constant R0, which is the resistance of the metal at standard temperature, the room temperature, for example, plus AT, which will be some fitting parameter that characterizes the slope of the resistance versus temperature characteristic. And then we have these higher order terms. For platinum 100, usually you can have just the linear 1 plus AT term times R0. But for example, in a data sheet for platinum 100, which is a type of platinum, and they define R0 as a resistance at 0 degrees centigrade, which in this case is 100 ohm. And then these are A, B, and C coefficients for these. But you will notice that how much smaller B and C are compared to A, 4 orders of magnitude. B is 4 orders of magnitude smaller than A, and C is 7 orders of magnitude smaller than part A. Even though it's temperature cubed, still these effects can be much smaller, depending over the range. It also depends on the range. But platinum 100, for example, is quite a repeatable material. So if you use it over the recommended temperature range, it keeps its calibration within the calibration parameters A, B, and C quite well for reasonably long periods of time. Okay, so then we can talk about now thermistors. Thermistors are basically based on semiconductor materials, metal oxide semiconductor materials. These are combinations of semiconductors and metals to form these metal oxide semiconductor materials. So let's say we have silicon and some material, chromium, cobalt, iron, manganese, nickel. Thermistors, interestingly enough, are absolute temperature sensors, which makes them quite unique. There are two types, negative temperature coefficient and positive temperature coefficients. The NTC, negative temperature coefficient thermistors, are really used commonly for precision measurements. And they have a negative temperature coefficient. Okay, so the resistance decreases as temperature increases, and you can see a plot of this for both types of sensors, and also the RTD sensor. So you see how nonlinear these thermistors are, although they can be calibrated. But the RTD sensor is extremely linear over this range from 0 degrees centigrade to 80 degrees centigrade. Then we have semiconductor thermometers, and basically the fact that that a PN junction is temperature sensitive, or a junction between two doped, basically one of these junctions has a temperature dependency. And this can be used as a temperature sensor as well. And then we have radiation thermometers, which are quite powerful. These depend on our heat transfer being proportional to the fourth power of the temperature that we want to measure. And basically, these are measuring electromagnetic radiation, right, in the far infrared ranges. And on the plot on the right, we see the excited power and then the wavelength range. This wavelength on the bottom plot of the plot on the right is in microns, so it extends from 0 to 12 microns is the wavelength. And then you can see that the temperature, as we go to these higher temperatures, we basically we have a broad spectrum that we can detect. The amplitude increases, but this peak then also shifts to lower wavelengths as well. Now, there are two ways that I'll talk about to measure this radiation. The first one is an optical pyrometer, and you can read the explanation on the bottom, and I mean in the text, but the picture on the bottom shows it, and essentially this is an interesting thing because it uses a tungsten filament, okay, and then it has a detector. So the detector is looking at a hot object, will have a certain color, and then there's a voltage source that's running current through a filament, just like an incandescent bulb. And there's a detector that then looks at the color of the filament bulb, and it matches the color of the filament with the color of the object that's warm. When those two match, then the temperature, when the two colors match, because these colors should match in the detector, then whatever voltage characteristic versus temperature that you have for the filament will tell you what temperature is being detected with the detector. This says eyepiece here. Okay, there are older instruments that you would actually just look into one of these pyrometers and then gauge the colors yourself, but now they have detectors here that are detecting these colors um, to be quite a relatively inexpensive way to measure temperature. Now, the other material is called a radiation pyrometer, and essentially this uses a detector that's sensitive to a certain wavelength of light. And there are many different types of detectors to measure infrared radiation. And these can be a photoconductive, so basically photons of a certain wavelength will create electron hole pair material. And then you can apply a potential and you can measure a current. So when you have a certain radiation, it generates current, just like a photodiode. But these are calibrated and work within the far infrared region. So the detector, essentially, the radiation will be focused with a particular type of infrared lens. And then the radiation comes in, and then you have an electrical configuration that detects either a photoconductive or a full voltaic type of detector. So different types of IR detectors are listed in this table. The y-axis is called a detectivity, D star, and this is basically the ability of the sensitivity of the detector. This is a measure for the sensitivity of the IR detector. And the x axis is in microns. This is the wavelength. So interestingly enough, you see this mercury cadmium telluride at 77K for the photoconductive types in the 10 micron range, which is room temperature, has about the best performance. There are these thermocouples, bolometers, and these things are very, very simple, but they don't have the same sensitivity as some of like the HGCD TE, which is mercury cadmium telluride. So the dotted lines on the tops are the ideals between the two types of detectors, the photovoltaic or the photoconductive. Now, for the last part of today's lecture, I'll talk about electrical test instruments, specifically a little introduction into a digital multimeter, specifically a digital voltmeter. And you'll see that it actually uses components that we've discussed throughout the lecture today, or this year. An oscilloscope, basic operation, basic components, and then the importance of the probe that you choose. And then also at the end, I'll briefly go over um, a spectrum analyzer and how it works conceptually. So we've all used a digital multimeter. Um, this is an analog voltage amplifier with adjustable gain. Now the gain of this thing is adjusted to match an analog to digital converter. And then it uses also high input impedances to minimize loading errors. So you remember we were analyzing errors earlier in the course. This is important now to see how these effects will come into when we're really doing a measurement. So, typical digital voltmeter has a configuration, and these switches are basically because it can do multiple functions. Okay, so the center feed is where you plug your cable into the voltmeter, and the shield is then will be your plus and minus. You can see there's a switch here. This 10 mega ohm will be our input impedance. For most of these systems, you can choose between 10 mega ohm input impedance to 10 or 100 giga ohm, depending on the type of measurement you want to make. And then we have an internal ground, so we can also pay close attention to how we ground the system with earth ground so that we don't get any floating potentials onto our measurements. We have a 5-volt reference, which is used for the A to D converter. Then we have a an amplifier. Basically, this is just a an amplifier to bring the signal back to some known level. Okay. So we have an analog input, and then the instrument will condition the signal. You can configure your input impedance to minimize errors for better measurement. And then the system will convert the analog signal into a digital signal, and then it will give you the display of the voltmeter. Now, in most of these instruments, it uses this dual slope integration to estimate the voltage at the input, even if it's an analog signal, because this thing can actually work with response times on the order of microseconds. So these things actually can respond to megahertz range signals. So if you see your digital voltmeter, it will have a range that it can detect. And so you know now how this dual slope integration works, and you can see then also these times the reference voltage is used for calibrating the reference of the system. Also, the reference defines your input range that you have for digital voltmeter, for example. So if you have a voltmeter, it doesn't have an infinite range that you can detect. It has a finite range that's determined by Vref. Also, most of these digital voltmeters, the common ones, will not allow you to go beyond 10 volts, between 0 and 10 volts typically. So this is probably one of the most common instruments that you'll see in the laboratory. This is an Agilent 34401A. This is a block diagram taken from the instrument's handbook. It is quite a sophisticated instrument, actually. It has many electronic components that are built into the system. The cost of this is quite high. It can be between 2,000 and 4,000 euro for this instrument. And you can see it has basically a computer, box number 1, the front rear selection, basically where you can choose all the functions of the system. Then the switches that we saw in the previous block diagram. Now this function switching allows you to choose the amplifiers, your input impedance, etc. And then we have block number 3 where we have the amplifier. Block number 4 is our AC circuit if we want to do AC detection. Block number 5 is the analog to digital converter. You can see also floating logic within this to do computations. The power supply for this system, you want to plug it in, but also you don't want it to be powered directly from the wall. It has an isolated power supply to run the logic within the system. And then it has a grounded reference circuitry as well to prevent floating potential due to, as we saw earlier, if you don't ground your system correctly, then you can introduce potential variations into different parts of the circuit. So As I say in this block, all measurement, control, and display functions are contained in the floating section. We have an A to D, changes the analog voltage into a digital representation, and then each measuring function converts the input to a DC representation. Now, in the loading error in this system, so essentially we get loading errors when when this Ri is either too high or too low, okay? Now you can see the error here if is basically this 100% times Rs divided by Rs plus Ri. Now, essentially, we want we want Ri to be usually as large as possible, and then our error becomes as small as possible. But you need to be careful because also if you make Ri too large, then also the noise at the input terminals also increases. So there's a balance between a large Ri and the noise that you can generate by making a really huge 10 gigaohm input impedance. But in general, you want to choose IR large so that your error that you measure between high and low is as small as possible. And you remember that from one of your homeworks when we calculated error for instrumentation. Now the common mode rejection, basically in this circuit on the bottom, you can see that when we do our measurement with the 34401A instrument, we have a high and a low terminal. And essentially the ideal meter separates basically the input impedance, and then there's always some charging capacitance associated with the multimeter. Now, if you're not careful, there can be a float voltage, which is represented as VF, that can give you a finite error in the measurement voltage, okay? And so again, in this case, the voltage error that you get, you want to have Ri as large as possible to offset these floating voltages relative to the earth ground of the instrument. So remember, when you plug your instrument in, you don't barely ground the system so it can float. So so when you're in a laboratory, it's best to have all instruments with respect grounded to an earth ground within the laboratory, so that you don't have these floating voltage configurations. However, unfortunately, most laboratories are not. So oftentimes, this can be a problem if Ri, our input impedance, is too low. Okay, then these can be more significant. Now, if you look at most instruments, you'll see that, like for example, in the 34401A Agilent instrument, it has connections for a 2-wire measurement and a 4-wire measurement. Now, in a 2-wire measurement, essentially, let's say we're going to measure some device, some resistor, our DUT, then we have to basically break the circuit and put current through our DUT. What you do then is you measure current through the connections to your device as well. So you're not just measuring the resistance of your device, you're measuring the resistance plus the resistance of the terminals. And this can introduce errors. So the 2-wire measurement, usually if you're doing typical types of measurements, 2 wires is fine. However, if you're doing measurements of devices where you're making where you have small measurements, or you're not really sure how the contacts are made, such as in semiconductor devices, you have to do what's called a 4-wire measurement, where you would have, you can see in the diagram on the bottom, you have a high and a low, and then a high sense and a low sense. So in the high and low terminals, you force a current through your device under test, And then you have another set of elements that taps in to only measuring the voltage. So this ideal meter has an extremely high input impedance. So no current, ideally, very small levels of current go through the high sense, low sense terminal connections. And this way, the effect of the terminal resistances is just contained in the high-low test current circuit, and you're just measuring the voltage across your device. So the four-wire measurement is a little more complicated, but you eliminate the effect of the test leads. Okay, now an oscilloscope, very briefly, obviously we don't have time to talk about everything about an oscilloscope. And oscilloscopes now have become, digital oscilloscopes have become amazingly easy to use. And you can see in this diagram, if you're interested to know some of the basic components of a system. It has an attenuator, a vertical amplifier, an analog to digital converter, of course, because most everything is digital now. And then it's a microprocessor also. And then it has these triggers and time bases that allow you to manipulate triggering of events that you can measure. So essentially, an oscilloscope measures, let's say, input current and output something. Okay, so it's a measure where it can plot voltage versus time, for example, current versus time, depending on how you're doing the measurement. And one of the most important aspects of doing a good measurement is paying attention to how you introduce the signal into the oscilloscope. And this is the channel input, where we actually have a probe, where we have a coax cable that we plug into the front of the oscilloscope, and then we want to clamp it to our circuit. Okay. Now, no probe or channel input will reproduce your signal perfectly. Okay, but you can adjust, choose the probe that best matches your circuit and your oscilloscope. Because essentially, the probe then becomes part of your circuit. So if you're measuring voltages in the time domain, or eventually in the frequency domain, then obviously resistors and capacitors are going to affect the signals that you're reading. Right? If you have something that's switching, if it's moving from a low level to a high level, ideally you want something that will be a perfect step function. If you have this capacitive charging function, you don't want that to be due to your probe. You want it to be a result of your circuit. So how do you decouple that? You have to choose the resistive and capacitive loading of the probe to match the measurement that you want to do. As an example, let's say that we have a probe, and the input probe consists of basically the CP and RP, and this is something that we can adjust. The CI and the RI are the input that's basically inside the oscilloscope, so these dotted lines basically show the probe. On the right side of the dotted lines, CI-RI, that's the oscilloscope. To the left is where you can your circuit. Okay. Now let's make a transfer function for this. So V in is going to be at the terminals between across CI-RI, and V out are the two unterminated lines on the left side of the circuit that's going to go to your circuit that you're measuring. So we can make a transfer function for this. I hope that you can derive something like this now in your transfer functions to be able to analyze this. Okay. Now for a 10-to-1 probe, then RP is equal to 9 mega ohm and RI is equal to 1 mega ohm. For low frequency, the loading factor can be reduced. Okay, so let's look at an example of this. Now, depending on how we do this system, ideally what we want is we want the time constant RPCP to equal to RICI. So if it's undercompensated, you can see that a switching function between high and low is going to be undercompensated if tau p is less than Ti. If they're properly compensated, then you're going to get, the input is going to be matched pretty well your measurement circuit. If you're overcompensated, if the tau p is greater than Ti, then you're going to get this overcompensation. And I'm sure that anybody that's measured signals with an oscilloscope, you've seen this type of an effect. And depending on the circuit that you have, sometimes you even have ringing on these overcompensated and undercompensated, because you can have actually second order transfer function depending on your circuit and in other configurations. So you have to be very, very careful just on the probe to make sure that you can probe these things in the proper way. And so that the effect of the signal that you see, the time-dependent signal that you see, is not due to the probe, but it's due to your circuit. And then you can see this is an example of an input probe and how to choose. And you can go through here what to use, what not to use, when to compensate in different frequencies. But essentially it's based on the transfer function, this little summary. So these are for passive probes. There are also active probes where you can amplify as well. So the probing functions are extremely important for oscilloscopes. Okay, now I'll talk about a spectrum analyzer. Spectrum analyzers are quite powerful instruments that allow you to look at the frequency content of time domain signals. So remember that we went over this little review where we looked at the Fourier transform, also Fourier series, and we can see that we can transform between a time domain signal into a frequency domain signal. If we have a sine signal, then we're going to get a single spike delta function at the frequency, the fundamental frequency of the sine signal, and they were offset in the minus and plus frequency domain. For a cosine signal, they were both in the positive direction. Now, a spectrum analyzer will do this for signals that obviously have multiple frequency components. Now, they're not accurate for frequency or power measurements. You can do real-time or swept frequency analysis, and amazingly, these RF instruments now can measure up to 100 gigahertz, which is quite powerful. Now, for the spectrum analyzer, you can look at modulation. So remember, we were looking at the synchronous demodulation where we had the DSB signal with our carrier signal. So you can see we can look at the modulation spectrum. We can look at noise, so we can look at the noise spectral density. And we can also look at distortion in our signal. You can see this example of distortion, and you can analyze the components. And why do you want to do this? Because if you have distortion or you have noise in your system, you can use this instrument to try to help you improve your system by identifying the frequencies of the distortion, the frequency of noise, and the power spectral density as a function of frequency allows you to tune the system to get better performance. So this is really an instrument to look at the frequency content of your signals that allow you to improve the performance. Now, a spectrum analyzer, really it's a Fourier processor. So we go from the time domain to the frequency domain. So a Fourier analyzer, essentially if we have an input signal, there's a filter that will simultaneously look at many frequency ranges, and when it gets amplitudes at a particular frequency range, it will represent that at a particular frequency range. So if your signal has multiple frequency content, let's say you have, in this case, a signal that has two sine signals that are modulated together, this instrument will go through this particular signal, and obviously there's a digital signal processor in the system too, and it can determine if the amplitude at a particular frequency is high at particular frequency locations by doing this filtering, very, very sharp filtering. Usually this is digital filtering over a very small frequency increments over a large range. Now this can also do filter sweeps, where you have one filter and you sweep over the frequency range, and then you can pull out the frequency components of your signal. Now this is a typical spectrum analyzer. This is an RF spectrum analyzer, so obviously for RF circuit design, these are extremely important. So it has a preselector, filter, mixer, a local oscillator to be able to look at the different frequency components, intermediate filter, sweep generator, detector, video filter, and then the CRT display is also really a analog to digital conversion. So the mixer essentially takes your analog input, and the local oscillator then mixes it, and then you get this intermediate frequency signal where you have your carrier and your original signal. And then the intermediate filter, where it does some filtering and then is able to basically isolate the frequency components. And then the detector combined with the analog to digital converter will pull out the signal and do processing on these things and put it into bins to be able to look at the frequency components. Now the video filter is basically a low-pass filter right before the analog to digital conversion. It does a smoothing function. And then at the end, it does the analog to digital converter. So this is just a diagram to show if we have, let's say, an input signal that has a frequency fs between 1 and 2 gigahertz, then the local oscillator is going to scan, let's say, from this 3.6 up to 6.5. You're going to mix these two. This thing is going to keep scanning. You can see our signal range and our local oscillator range, and then we have this modulated signal. We're going to have FLO, FS, FLO. We have our sidebands with minus and plus, and then we put it into our intermediate filter where we pull out the 3.6, go to our detector, analog to digital conversion, and you'll see that we'll pull out, so 0 would have been our 3.6 gigahertz oscillator signal, and then we pull out our signal Fs at the output of this system. This is an example of a very expensive, but not too expensive. It's about the cost of a new automobile, but okay, it's not terribly expensive. RF spectrum analyzer. You can read some of the specifications here if you're interested, if you're going to do RF design. Very, very important instruments for not only looking at RF design, but looking at noise or nonlinear distortion, or even transfer functions of systems. These things can really look at the frequency content of time domain signals that allow you to do better designs. So this is the conclusion of Lecture 10 and the conclusion of Meettechniek 2013-2014. As I said, please read the announcements for the course. I'm going to be giving some general updates on the final exam content. Thank you. I hope that you enjoyed the class. It was not optimal having to do the class just with video lectures, but I hope that you learned something in Meettechniek this year. And if you have any questions about any of the content, any of the lectures, you are welcome to send me email before the class is over. And please study the homework assignments and the homework solutions and Lecture 10, primarily temperature sensors, for the final exam. Thank you.